Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani from Department of Computer Science, Aribhat College, University of Delhi. So presently in our series of operating system, we are discussing the topic of memory, and basically memory management is the precise topic which we are discussing. And in today's lecture, what we are going to discuss is about how this memory is being allocated, and what are the other processes behind it. So when we talk about the main memory allocation, basically main memory is required for two entities. One is our operating system and another one is whatever various user processes are going on. So let's say if we are talking about multi-programming, then in multi-programming there are various processes which are being loaded into the memory. So those user processes I am talking about, and another entity is the operating system. So for this, your memory is basically if we want to understand the simplest layout, that how this is going to happen and how is this allocation is occurring. Basically, this main memory is being divided into two partitions. One is for operating system and another one is for your various user processes. Now, your operating system could be in either low memory or high memory. That is actually, we can say it's a kind of choice, but basically or generally we can say your operating system is kept into low memory. Why? Because your interrupt vector resides in low memory, and when your interrupt vector is residing into low memory, that becomes a deciding factor of operating system being there. Then if we talk about continuous memory allocation, so basically your memory is being taken up in continuous slots by the processes. So continuous memory allocation is being taken, and each process within this continuous memory allocation, each process is contained in a single section of memory that is continuous to the section containing the next process. So basically, for example, say if high memory area is given to various user processes, then the first process where it is going to end, the next process will take up the memory which is starting continuous from there. Now, if these various processes are being stored or given the memory one after another in in a continuous fashion, now what is the probability here, or what is the danger here? So danger here is mixing of one process into another process, or mixing of data of one process into another process. And what we want to do, we actually want to prevent this mixing. We also want to prevent one process from accessing the memory and the data of other. How are we going to do it? For this, we have already seen two of the concepts. One is the relocation register and another one is the limit register. So these two kind of entities are there as the saviors here, where we have a system with relocation register together with a limit register. Then in that situation, these are some these are registers which are going to give the limits on which particular memory will be accessed by which of the processes. So what is actually happening here is, it is your CPU scheduler who is going to select a process for execution from the input queue. Now, whenever this CPU scheduler has selected a process for execution, the dispatcher component is going to load the relocation and the limit registers with their correct values, and this is actually happening as a part of the context switch. So please recall, the context switch is taking one process from memory, giving it to the CPU, and relocation or we can say taking out of CPU from one particular process. So the dispatcher loads the relocation and limit registers with the correct value for that particular process which is being which is going to be executed now. Every address generated by the CPU is checked against these registers. So whether these addresses are valid or not with reference to that particular process, we can say will be checked against these registers. Both the operating system and the user processes, user programs and the data can be protected from being modified by this running process if correct value of relocation registers and limit registers are kept, and these are to be checked while before accessing any particular memory. So relocation register scheme, basically we can say this relocation register scheme is going to provide an effective way to allow the operating system's size to change dynamically. So till this point what we have seen that this relocation and limit registers are there to save us from one process accessing the memory of the another. Fine. But this is also an effective way to allow operating system's size to change dynamically. Now the question arises, how operating system's size is going to be changed and what is the role of relocation register scheme in that. So basically if you are aware that the operating system as an entity contains some code and some buffer space for device drivers. Now this buffer space which is there for device driver is used whenever a device driver is we can say is being used. So basically a device driver or any other operating system service for that matter, when not in use commonly or generally, it is not a good idea to keep the code and data corresponding to that service into the memory, because that is not being we can say commonly used or frequently used. So that such code which is not being used commonly and hence it is not kept in the active memory, this code is sometimes called the transient operating system code, and this transient operating system code comes and go back as and when needed. So the point here is, it is not only the user processes which are being accessed on a need basis or for which the memory is accessed on the need basis, it is also operating system and its services that are kept into the memory on the need basis, and these are basically known as transient operating system codes. So yes, using the code changes the using this transient operating system code is going to change the size of the operating system during an program execution. So whenever a code is required, it is being loaded into the memory, the size of operating system increases, and vice versa. That means whenever it is not required, it is not kept into the active memory, the size of the operating system is we can say decreases or kind of shrinked. Now this was basically the idea that what is actually happening inside the memory and how it is happening. But before all these things takes place, there is one step of allocating the memory as in what is the method through which user processes are going to get their slots within the memory, or this operating system is also going to get its slot into the memory. So there are methods for memory allocation, and the simplest method for allocating the memory is to divide the memory into several fixed size partitions. So whenever various partitions are being done and all these partitions are fixed size, now here is a rule that each partition will contain exactly one process in order to we can say avoid the overlapping. So now the question comes up that what is the degree of multi-programming, what could be the degree of multi-programming in such systems. So, we can simply say that degree of multiprogramming in such systems where the memory is divided into fixed size partitions. So, the degree of multiprogramming is bound by the number of partitions. So, the number of partitions will be kind of equals to the degree of programming, or even we can say lesser, because we need to allocate one partition for our operating system also. So, basically the correct statement could be the degree of multiprogramming is bound by the number of partitions. Now, in this method, when a partition is free, a process is selected from the input queue. Please recall that all the processes which are waiting for the memory are kept inside the input queue. So, one process is selected from the input queue and is loaded into the free partition whenever the partition is free. Now, another situation could be there is no free partition, but before that we also need to see that whenever the process terminates, it is kind of, we can say, deloaded from the partition. The partition becomes available for another process. So, whenever it is required, the process is loaded into the partition. Whenever the process terminates, it is taken out from the partition, and hence now the partition is available. Now, one situation here could be, it is possible that the operating system is going to, or one particular job, one particular process is looking for some partition to be free, because that process needs itself to be loaded and then executed, but the point is the partition is not free. So, then in that situation the process has to wait, and this will be communicated to the process through operating system. Now, another scheme could be variable partition scheme. In this scheme which we have seen till this point was the fixed partition scheme, and in this fixed partition scheme the size of the partitions is fixed, and one process is taken, one partition is allotted, and then so on and so forth. But now, on the other hand, we can have a variable partition scheme. This partition scheme of operating system keeps some statistics or some records. So, basically it keeps a table indicating which part of memory are available and which are occupied. So, initially if we can see, when nothing is being loaded, the whole memory is available for the user processes, and it is considered as one of the large blocks of the available memory, and this large block of the available memory is known as whole. So, eventually when processes start coming and memory contains a set of holes of various sizes. So, what is happening, one particular memory has taken, one particular process has taken some memory, another particular process has taken another slot of memory. So, these are basically this process is going to create holes of various sizes, and at any given point of time we have a list of available block sizes and an input queue. So, whatever is happening, we have an input queue. From that input queue, the process is ready to get loaded into the memory, and whatever the available memory is there in terms of block sizes, whatever the that list of available block sizes is also available with operating system. So, on one side we have an input queue whose elements are the processes which are looking for various memory which are looking for various memory addresses, or on the other hand we have a list of available block sizes, and the operating system can order the input queue according to a scheduling algorithm. So, the sequence of the input queue could be according to a scheduling algorithm, and one process has been taken and memory is allocated to the processes until no available block of memory is large enough to hold that process. So, one thing could be there, that there is memory which is available, but it is not large enough so that the requisite process can be given that memory, or it is not large enough to hold that process. So unless this type of a situation comes up, the memory is kind of, we can say, the operating system is going to keep pace with allocation of memory. But now one stage comes up that memory is not sufficient memory is available, then the operating system has to wait until a large enough block is available. That is one thing. Or another idea could be, the operating system can look for a process whose requirements can be fulfilled. So for example, we have let's say 50 units of memory, or let's say we have 50 MB of memory, and there are processes who are requiring 60 MB and 70 MB of memory. So these two processes of 60 MB and 70 MB cannot be kind of allocated in a block size of 50 MB. So operating system can skip down the input queue and to see whether there are processes which are having some smaller memory requirements, which is less than equals to 50 MB, so that these requirements can be met, and we have our processes keep on going. So but this during this process, actually, if you can see what is happening, the memory blocks available comprises of a set of holes of various size scattered throughout the memory. So initially there was one hole, and now we have started allocating the memory from that particular big hole, and this memory is also coming back as in kind of getting free as and when not needed, or as and when the process is getting terminated. So basically now there will be different size of holes which are scattered throughout the memory, and when a new process comes up, the operating system needs to search the set for a hole that is large enough for a particular process to be loaded. Now if it is going to find kind of, we can say, one hole which is large enough for the process that is given. Now another situation could be, here is the hole is too large and it is splitted into two parts. So one part is allocated to the process and other is returned to the set of holes. That means other is returned to the kind of free memory which is in the available set of the memory. Now we can compare this scheme with the fixed partition scheme. In the fixed partition scheme, the size of the partition was fixed and it was not supposed to be changed, but here if the hole is large enough, it can be splitted into two parts. So basically let us try to recap what we have gone through in the lecture till this point. So we have seen what kind of allocation this memory is going to take in case of multiprogramming. So if we talk about continuous allocation, so there will be some operating system and then some user processes residing inside the memory in continuous fashion. That is one idea of memory allocation. And within this idea, how are we going to make sure that one process will not mess up with or will not interrupt into the data of the another process? That is with the help of limit registers and relocation registers that can be done. Now this was the story of what is actually happening, how this memory is going to be allocated. Now what are the strategies for kind of partitioning the memory? So we have seen one could be fixed partition scheme, in which blocks are having their fixed sizes and the processes will be taken up from the input queue and will be given to these blocks, and so on and so forth. Another one could be the we can say dynamic partitioning, variable partitioning scheme. In this variable partitioning scheme, the size of the blocks or size of the holes can be we can say is variable and can be changed on the fly also. And within this process, now let's take the lecture further. Now if one part is allocated, I am talking about the situation where the whole is too large and it is splitted into two parts. So one part is allocated and other is returned to the set of holes, and when a process terminates, it obviously it is also going to release the block of the memory, and when which block is being released is also placed back in the set of hole, we can say. If the new hole is adjacent to the other holes, which is not necessary. If it is happening, the new hole, that means the memory location which has got freed just now is adjacent to other available memory locations, it is going to be merged at this point. This is, and now why it is merged, so that we can have a kind of big hole as we have initially. So at this point the system may needs to check whether there are processes which are waiting for the memory and whether this newly freed and the recombined memory could satisfy the demand of any of these waiting processes. So some chunk was left unused. Why it was left unused? Because it was small in, or it was small enough so that it was not able to satisfy any of the requirement of any of the process. Now we have got one more hole which is just got freed and these two holes are combined. So let's say for example earlier the 10 MB was there and now we have 10 MB more. So now there is 20 MB in continuation. Of course, that is what I am talking about. The other scenario will be discussed shortly. So now we have this 20 kind of 20 MB of memory, and we will check in the input queue, or operating system is going to check in the input queue that whether this total chunk of 20 MB is good enough to satisfy the requirement of any of the processes which are waiting. Now this is actually, we can say this variable partitioning scheme or dynamic storage allocation problem. The basic we can say problem or the basic concern here is how to satisfy a request of size n from a list of free holes. So basically what kind of strategies we are going to take up while we are allocating the memory. So the concern is how it is being satisfied, or how to satisfy a request of size n from a list of free holes. There are solutions, or there are techniques to the solution of these problems. Basically three kind of allocation techniques, we can say. These three are named as the first fit, the best fit and the worst fit strategies. So now we will look into all these strategies one at a time into detail. So when we talk about the first fit, and the scenario in which we are discussing is about dynamic storage allocation and how to satisfy the need of a particular process or of various processes among whatever is available, what size of holes are available. So the first fit strategy says that allocate the first hole that is big enough. You start kind of looking into the size of looking into the holes, and whatever size is going to fit for that particular process, and that is the first one which you have found. So allocate the first hole that is big enough for that particular process. We are also going to see examples of this in a short while. Now for this, searching can start either at the beginning of the set of the holes or at the location where the previous first fit search ended. That means in kind of we can say in a list where the actual pointer is, or it can begin from the or it can start from the beginning also. And as soon as your first fit is going to have one particular slot which is good enough, which is big enough to satisfy the requirement of the process, we will stop searching. So here we can see this first fit allocation in our operating system, that for example, we are looking for, there are process blocks of P1, P2, P3 and P4, and the requirement is 90, 50, 30 and 40. So, whatever, let us say for example, we are going to take one particular the first one, which is 90, which is looking for some 90 units of memory, and within this 90 units of memory we will start searching in the block which is given at the bottom. So, first block is of 20, so we cannot allocate here. The second block which we are finding is of 100, and we are kind of happy to have it, because 100 is good enough to accommodate one process or process P1 of size 90, but the memory wastage here is going to be 100 minus 90, that is equals to some 10 units or 10 MB, whatever. Coming to the process P2, the process P2 is of 50, so we are going to check 20, it cannot allocate. 100 we have already allocated. Then we kind of don't have enough space in the third block, which is 40. So now for the process P2, which is having a requirement of 50 units of MB, the first fit which we are going to have is of 200, the block number 4, which is of 200 units. So process P2 is now residing into this here block number 4, and here is a kind of, we can say, wastage of kind of 150 units of memory, because the requirement of process P2 was only 50, and the first fit which we have got is of 200 units. Coming to the process P3, we cannot allocate 20 here because that is lesser. 100 is already allocated, and now we are left with block number 3, which is of 40. So that process is actually given this block which is of 40 units. Now what is happening here is 40 minus 30, which is 10, the 10 units of memory are being wasted here. So here we can say block 2, in which the process P1 is residing, is wasting 10 units of memory. Process P2, which is residing inside the block, is wasting a lot of memory, which is kind of some 150 if the requirement is of 50. Then process P3, which is residing inside the block block of 40, which is block 3. So 40 minus 30, 10, it is also wasting. But the agony here is the fourth process, which is having a requirement of 40 units of memory, will be unallocated because of this strategy of first fit allocation. So now till this point we have clearly got the picture that this is the strategy which is not very efficient in allocation of memory. So let us try to recap what we have covered in this lecture. So how is this memory is being kind of allocated, what are the various techniques for the allocation of memory, and in case of dynamic partition, in case of dynamic allocation, what are the techniques through which a block of the memory is going to be kind of selected for the allocation of memory, that is best fit, worst fit and first fit. And among these three techniques we have covered one technique, which is the first fit technique. Now best fit and the worst fit, and upcoming topics of fragmentation and segmentation we will be taking in the next lecture. Here is a list of references which is being used for the preparation of lecture. Hope you have enjoyed it. Thank you for a patient hearing. I'll see you in the next lecture. Till then, goodbye.